So we're always hearing about this paradox in AI. To get smarter models, you just have to make them bigger. But what if that's not the whole story? What if there's a better way? A new paper is suggesting a path to AI that's actually smarter, not just bigger. And to help us break it all down, we've brought in an expert. So let's get right into it. All right, so let's start with the big question. Why is this bigger is better approach suddenly causing so many problems?
Yeah, that's the key question, isn't it? Because for the longest time, it worked incredibly well. I mean, just scaling up models unlocked these amazing new abilities. But now, we are hitting a very, very hard and very expensive wall.
And that wall is, simply put, cost. The amount of raw computation, the sheer memory required, not to mention the energy needed to train and run these massive, massive models, well, it's just becoming unsustainable. It's a huge bottleneck that's really limiting who can even participate in this kind of cutting-edge AI research.
Right, so the race to build the biggest model is basically pricing a lot of people out. So what's the research community doing to try and get around this?
Well, broadly speaking, the field has kind of split into two main camps. The first is what we call parameter efficiency. This is all about finding clever ways to reuse parts of the model, the parameters or the weights, so you just don't need as many. You know, think of it like using fewer but more versatile tools. The other camp is adaptive computation, and that's all about working smarter, not harder. Basically, it means the model only uses as much computational power as a specific problem actually needs.
And I'm guessing the holy grail is to somehow combine the two?
Exactly. But getting them to work together, in one elegant system, that's been the real challenge. And that is exactly what this paper is all about. It introduces a brand new framework called Mixture-of-Recursions, or MOR for short.
Right. And what's so exciting about it is that MAR really is this big attempt to finally unify those two efficiency approaches into one single cohesive system.
So in simple terms, what exactly is Mixture-of-Recursions?
Okay, so at its core, it's something called a recursive transformer. Now what that means is it has one shared set of layers and it just reuses them over and over again. But the secret sauce, the really clever part, is this lightweight router that looks at every single word, every token, and decides how much thinking time that word deserves. Simple words, they get a quick pass. More complex ones, they get a lot more processing.
And what's so powerful about this design is that Moore pulls off three key efficiency gains all at the same time. It ties the weights together, which cuts down the model's size. It routes the tokens, which cuts down on all that unnecessary computation. And it cleverly caches information, which reduces memory and just speeds the whole thing up. It's really like a three-pronged attack on inefficiency. Okay, so that's the big picture. But I really want to get into the details of how it thinks. Like, what does this intelligent routing actually look like in practice? This table here gives us a really great, simplified example of that. Just notice how different words or tokens get a different number of recursion steps. So a simple common word like feel might only need one shallow pass through the model. But a more complex concept like confident or a proper noun like drugs gets 3 deep passes. The model is literally learning to spend more thinking time on the words that actually matter the most. So it's almost like an intelligent triage system in a hospital. A scraped knee gets a quick look from a nurse, but a really critical injury gets the full attention of a whole team of specialists.
That is the perfect analogy. It is all about allocating your resources dynamically, based on the actual need.
So that router has to make these critical decisions. How does it actually do that?
Right, the router has to make these decisions somehow, and the paper actually explores 2 main strategies for this. One is called expert choice, and the other is token choice. Let me break down the difference for you.
Okay, so with expert choice routing, each step of the recursion acts like an expert. It looks at all the active tokens and basically picks the top few most important ones to continue on to the next round. So the pool of active tokens gets smaller at each step. Now, with token choice, the decision is made completely up front. Each token is assigned its entire processing path right from the very beginning.
Got it. So one is like a step-by-step competition, and the other is more like a pre-assigned itinerary.
Exactly right. And this dynamic routing also lets the model be way smarter about memory management. So the paper proposes 2 strategies, and you really don't need to worry about the formulas here. The key takeaway is the trade-off. Recursion-wise caching is sort of a balanced approach that saves memory by only keeping the active tokens around. Recursion sharing is way more extreme. It saves the absolute most memory, but you pay for it with a bit more computation.
So it's that classic engineering choice between saving memory and saving time.
This all sounds incredibly clever in theory, but, the real question is, does it actually work? Let's get into the data. Okay, so here's the headline result, and it's a big one. The researchers found that their Moore model could get better performance than a standard model while using almost 50% fewer parameters.
Wait, 50%. That is a massive, massive gain.
It really is. I mean, just look at these numbers. The Moore R model, with only 167 million parameters, scores a 43.1% accuracy. That's actually better than the standard vanilla model, which needed 315 million parameters just to get to 42.3%. Wow, so it's not just smaller, it is demonstrably smarter. And does this advantage hold up when you start talking about really big models?
It does. That's what's so important here. The advantage holds up as the models get bigger. This chart shows that across multiple scales, all the way up to 1.7 billion parameters, the Moore models consistently match or even beat the standard transformers. It really proves that this architecture is truly scalable.
Okay, so it's more parameter efficient, we've established that, but is it any faster?
This is where it gets really, really impressive. When it comes to actually generating answers, what we call an inference, the MAR model can be up to 2.06 times faster than the standard baseline. So it's not just more efficient, it's significantly quicker.
Okay, these results are pretty stunning. Let's zoom out a bit. What does all of this mean for the future of AI development? Well, the implications are just huge. First, Moore establishes what we call a new Pareto frontier for efficiency.
Quick pause. For those of us who might not be familiar, what's a Pareto frontier?
Of course, it's really just a technical way of saying that it sets a new benchmark for the best possible trade-off between performance and cost. So it proves you can get that large model quality without the massive large model cost. It's scalable, and it even lets you dynamically add more thinking time during inference to get a higher quality answer on the fly. I also heard there was a pretty surprising finding about the best way to make these models even better.
Yes, this was fascinating. With a standard model, you can often improve it just by showing it more and more data. But for Moore, the better strategy is actually to increase its parameter count, making that shared block of layers more powerful, rather than just feeding it more examples. The paper calls it a capacity-hungry model, not a data-hungry one.
Now, to be balanced, every single study has its limits. What did the authors themselves say they still need to figure out?
Oh, they were very clear about that. Their experiments only went up to about 1.7 billion parameters, so proving this at the massive scale of today's frontier models is obviously the next step. They also want to find better ways to control the capacity at each step, and of course test it more rigorously on really complex reasoning tasks.
There's a quote from the paper that I just found really profound. It says, "The model learns to allocate recursion depth based on semantic importance. It thinks harder about more meaningful words."
And that really is the core takeaway, isn't it? This isn't just some clever engineering trick. The model is genuinely learning to focus its finite cognitive resources on the parts of the problem that actually matter. It's a real step towards a more intelligent, more efficient form of thinking.
Which really just leaves us with one final thought. Frameworks like this one, like Mixture-of-Recursions, they show a really clear path toward models that aren't just bigger, but are fundamentally smarter about how they work. And it really begs the question, is this the future? Will this kind of adaptive token-level computation soon become the standard for how we build all artificial intelligence?